As the water in channels moves, it will encounter a great deal of frictional resistance by the bed and by the banks of said channel. The cross-sectional shape, which is pictured as a slice taken from the channel, will determine to a very large extent the amount of flow that is in contact with the banks of the channel or with the bed of that channel. So overall, it will determine the frictional resistance that it will have. So the measurement of that contact is called the wetted perimeter, okay? Wetted perimeter. So perimeter that has been wet. A stream that has more wetted perimeter will have a greater frictional resistance and will make the stream overall a little bit slower. A stream that on the other hand has less wetted perimeter will have a lower frictional resistance, which will make the stream flow faster. So, typically speaking, a stream will flow faster if the width and the depth are nearly the same, rather than if the width is very large and the depth is very small, or the other way around, where the depth is very large and the width is very small. This second case is not very common in nature, but theoretically it could happen. So if you picture a stream where the width and the depth, or the width and the depth, is 5 meters by 5 meters, the overall wetted perimeter is going to be less than if the stream had a width of 10 meters by a depth of 2 meters, or a depth of 10 meters by a width of 2 meters. So overall, it's better if the width and depth are close to the same, making the wetted perimeter be as low as possible, so there's less frictional resistance and a faster flow. Another aspect to have in mind about the channel shape is the place at which velocities will be greatest. So in a symmetrical channel, or at least a symmetrical part of a channel, the greater velocities will be near the surface towards the middle of that channel. So in a channel like this one, where it's relatively symmetrical, both sides are relatively at the same angle, then the greatest speed will be here at the surface of the channel in about the middle part in terms of the width. On an asymmetrical channel like you're seeing up here, the greatest velocities will be also at the surface, but in this case they will be over the deepest parts of the stream, which for this channel's cross-sectional view will be closer to the left bank of that channel. So in this case, again, it's on the left. However, if it's a different part of the stream, it could be on the right. So this type of asymmetrical shape will appear typically on areas of the channel that are on curves. So in this curved area, for example, it's expected that a deeper part will lie closer to this bottom part of the stream channel, and then a shallower part will lie here to the north, part of the channel. Channels will be the fastest when they are bank full, meaning right before the water is so high that it inundates the floodplain. It is at this point when the ratio of the wetted perimeter to volume of the water, area of the water on a cross-sectional view, will be the lowest. So the overall perimeter that is wet on that cross-section is lowest when the water is close to inundating that floodplain. Another factor is how rough a channel is, another factor that will influence the velocity. Channels that have a lot of boulders, for example, or irregularities or obstacles like tree branches, will typically be reduced in speed because all of these obstacles are going to create a hindrance to the flow of that stream. So the less rough a channel is, the faster it will flow. And the more rough, the slower it will flow. Overall, streams will vary in size from small headwater creeks, which are less than a meter wide or so, to large rivers with widths of several kilometers at times. This is largely determined by the amount of water that is supplied from the drainage basin. The measure that is most often used to compare the size of streams is discharge. So discharge is the volume of water that flows past a certain point over a given unit of time. It is typically measured in cubic meters per second or cubic feet per second, and it is typically determined by multiplying the channel's width times the channel's depth at different kind of semi cross sections, and then multiplied by the velocity of flow at that specific point. So that's why the units are going to be some sort of distance that is cubed. So width times depth times the distance part of velocity over some unit of time, which would be part of the velocity measurement. So, for example, a channel that has a width of, say, 10 meters and a depth of 5 meters, and that is flowing at a speed of 2 meters per second, will have a discharge of 100 cubic meters per second. 10 times 5 times 2 will give you 100, and because the velocity is per second, then it's overall 100 cubic meters per second. The discharge of a river typically will change over time because of variations in the amount of precipitation that is received by the watershed. So typically at gauging stations, the width and the depth are known and monitored, and they tend to change a little less than the speed will. But of course, they do change with changes in precipitation. So many a times changes in seasonal in seasons will change the depth and the width at which the stream is flowing. An example that we have is the one that I'm representing here in the slide. So here I show you the discharge from the Boise River, which is measured at the Glenwood Bridge. So the image on the left shows you that discharge represented for the seasons of, I guess, spring and summer of 2018. And then the image on the right shows you those same seasons for 2019. So obviously the discharge measured at the Boise River is highly human controlled by the dam that is upstream, but it's still a pretty good measure to check the changing amount of water that was received last year to the one that was received this year, and how we had to control when to let the water flow from the dam. So as you can see, last year the discharge was greater in the spring months, but lower in the summer months, which is partly why floating the river opened up a little bit earlier last year than it did this year. So currently in July, you're seeing that the discharge is of about 1,000 cubic feet per second this year, and last year it was about 800 cubic feet per second. So a little bit higher this year than last year, because we did receive a little bit more snow melt this year than last year. So the table that you see here is a table compiling the 10 largest rivers in the world, and this is based on discharge. As you can see, the Amazon River is by far the largest river, 5 times larger than the second largest, which is the Congo River, and it is about 12 times larger than the Mississippi River, which is America's largest river. So the USGS maintains a network of about 7,500 stream gauging stations within the country, and one of those stations being the Glenwood Bridge station that we just saw for the Boise River discharge measurements. These stations will overall collect the basic data about the country's surface water resources on a daily basis, basically. So there are a few ways in which the changes of a stream may be monitored. One is through monitoring the stage. The stage is the height of the water surface relative to a fixed reference point. So usually this measurement of stage is mentioned by the media when there is a flood stage, meaning a stage where the level of the water is so high that it will flood over the banks of the river, that it will inundate the floodplain. So stage is basically how high the river will be relative to the reference point. Another way to examine the changing stream as it gets further down is called the longitudinal profile of a channel. So this is going to be basically a cross-sectional view of a stream from its source or its head to the mouth or the point where the stream meets another larger stream or an open body of water. So the image on the left over here shows a pretty obvious and typical longitudinal profile. So this type of typical longitudinal profile will have a kind of concave shape to it in the graph, where the y-axis is going to represent the elevation, and then the x-axis is going to represent the distance inland. So in this case, you see that there is a decrease in slope that occurs at the headwaters region that is much greater than the decreasing in slope that you see in the trunk section and then closer to the mouth section of that stream. In most stream profiles, longitudinal profiles, like in the image that you see on the right, you will typically see an increase in the discharge the closer you get to the mouth of that stream. You will see a decrease in the roughness the closer that you get to the mouth of the stream, and you will also see a decreasing of the slope, as we saw in this image. Same thing happens as a common rule for most of the streams. So if you, and you see also an increase in the channel size as you get closer to the mouth. So if we account for all of these factors, it is relatively a rule of thumb to say that the flow velocity will increase as the channel approaches the mouth of the stream. Or if you want to say it another way, it is lower velocity closer to the headwaters region, and then higher velocity closer to the mouth or the outlet of that stream.